Hey, Science 8s, it's Manchak here with your first lesson in our new online Science 9 course. I hope you all had a good spring break, and we're going to get into recording this lesson right now. Just a couple of things to keep in mind as we go through this. First off, make sure that you've got your notes in front of you. We're going to be going through concept C4, which has to do with the electromagnetic spectrum. So have that in front of you, highlighter, pencil, something along those lines. If you don't have your notes with you, that's fine. Go onto the Google Classroom right now and go to the classwork page under Unit C, find resources, and where it says notes and worksheets, click on that and download your notes, and then have them sitting beside you. Maybe split your screen or something like that and watch this video on one screen and have a look at your notes on the other screen. So the way this is going to work is I'm going to run through the slides that we normally would do in class. I'm going to talk about the different things that I think are important for you guys to know from this section, and I will ask you to pause at some points and maybe take a minute to look in your textbook and do some questions, or maybe look at a video or something like that online at some point, which I'll have some resources for you there as well. So take your time going through this. Remember, this is just one portion of what I want you guys to be able to do or for this concept. We're going to do a concept a week, which means that this week's concept is C4, next week will be C5, and so on. I would expect to be posting tomorrow, or maybe the maybe later in the week, for some formative questions as well that you can do through Google Forms. And then I will also post a summative quiz. That one will be for marks later on in the week that you can do and sort of wrap everything up for the concept before we move on to C5. Move on through this at your own pace. Whatever's going to work for you, let it work for you. Okay, and as always, if you have questions, please track me down via email or pop by my office hours, which I'll post online later today. So I am going to just slide this out of the way, go to my presentation, and just quickly slide this back where I want it. Okay, perfect. So we had already started to go through this before spring break, but I think it's important for us to run through it again, especially the beginning parts of it again, because we took some time to do it. We had some great conversations, some goofiness as I recall, but I want to just run through this with you just to make sure, all the way through, just in case somebody missed any. We may as well start from the beginning, right? So concept C4 is all about the electromagnetic spectrum. It's a relatively short concept. What you guys are seeing here is the objectives I hope you'll be able to do. So we're going to talk about the nature, we're talking right now about the nature of light and vision. We're actually going to get into talking about eyes in concept C5, so that's coming up shortly. But I want you guys to be able to describe the characteristics and composition of sunlight, explain the wave properties of light and the electromagnetic spectrum, and then describe some applications and hazards of the electromagnetic spectrum and electromagnetic radiation. So that's our goals for this concept. I'm picking and choosing what I think is important in these sections, so I'm skipping over a bunch of stuff because there's a lot of content, and if we went through all of it, we may start to run out of time, and we're already a little bit behind as it is. So I'm going to pick and choose a few bits and things. So the wave model of light, we talked about this before. The wave model of light is used to help us understand what light really is. So far, we've been able to see light as, we've talked about the four properties of light, right? We talked about that it can bend. We talked about it that it reflects. We talked about the fact that it travels in straight lines. Now we're talking about that fourth one, which is that it's a form of energy. And this form of energy comes in the form of a wave. And basically this wave model describes the characteristics and behavior of light energy. And it describes light as energy in the form of waves that come in different lengths and frequencies, resulting in the different color of light. So what you're seeing at the bottom here with this prism is we've got white light coming in. That white light would be the light that would come from the sun or from a light, for example. And as it travels through a prism, that light gets scattered by the prism and separated out into the different waves of light. And I don't know if you can see it, and maybe if you're not at full screen you might want to go a little bit bigger, but you can see that the red light is over here and the violet light is down here, so it goes red, orange, yellow, green, blue, indigo, violet. And you can see that the wavelengths are much longer on the red light and much shorter on the purple light, but the frequency is much greater on the purple light and much less on the red light. You may want to come back to this and watch it a couple of times too, just because it's kind of cool. So let's talk about waves first before we get into that. So to understand the wave model of light more deeply, we need to spend a little bit of time exploring waves. Waves are, that structure. You can think of the, throwing a rock into a calm pond, and how the waves move out from this where the rock goes in. And those waves have what we call peaks and troughs. The peak being at the top, the trough being at the bottom. And the waves have different components, and we'll talk about what they are right now. The three components these waves have are wavelength, frequency, and amplitude. Wavelength is the distance from one crest or peak of one wave to the next wave. So I'm going to go to this really quickly and show you. So this is a peak or a crest, and this is the bottom or the trough. I like to go peak to peak, and this is a wavelength from one peak to the very next peak. Down here, this is a shorter wavelength from one peak to the very next peak. I told you guys this, don't worry about this symbol here. That's the Greek letter lambda, and that's used to represent wavelength when we're dealing with questions like this, physics like this. So wavelength is how long each wave is, long or short depending on the wave. And then the other thing to understand is frequency. Frequency is the number of times the medium vibrates in a given unit of time. And the way I want to kind of look at this is frequency is how many full waves are we getting per second. And let's imagine that this blue line that goes across here represents 1 second. Same with this one. This also represents 1 second. So this light over here, this wave over here, is traveling at a low frequency. We're really only getting 1, 2, and a bit wavelengths in the second. Whereas this one, we're getting 1, 2, 3, 4, 5, 6, and a bit, probably 7 wavelengths in 1 second. So this would be low frequency, and this would be high frequency. Hope that makes sense. The last thing to talk about is amplitude. And amplitude is the height of the wave from the rest position. And that we're not going to talk a lot about it, but the amplitude is, this is rest position here, and the amplitude is that height there, or that height there. And these are both experiencing the same amplitude. This last bit at the bottom here, I think I asked you to highlight in your notes when we went through this. This is really important. The longer the wavelength, the smaller the frequency, or the lower the frequency. So they work opposite to each other. If your wavelength increases, your frequency decreases. If your wavelength gets shorter, your frequency gets higher. Okay? And we can sort of see this in this diagram. This is long wavelength with low frequency. So long being a big measurement, low being a short measurement. And this is short wavelength with high frequency. Short being a small measurement, high being a big measurement. So this diagram here I think is really important, and I hope you guys take the time to have a look at it. All this is leading us is talking about light, and light comes in a couple of different forms. We see light as what we call visible light, the stuff that interacts with the rods and cones in the back of our eyes and allows us to see. But there's other forms of light out there, other parts of the electromagnetic spectrum that allow us to, that we can make do work for us, that we've created technologies around that allow us to take advantage of them. So what you see in front of you right now is the electromagnetic spectrum. And we know that light travels in waves. We just talked about that. And these waves come in a spectrum of different wavelengths and frequencies, what we call the electromagnetic spectrum. Normally I break the word down. So electro is referring to electricity or electrons, and magnetic is referring obviously to magnetism in some way. I would go into talking about what electromagnetic actually means and how they work, but I think it's a little beyond where we need to be right now, and there's no need to add that. What you guys are seeing here is the electromagnetic spectrum, and it's a little bit complicated, but what I really want you guys to get from this is that, first off, what we can actually see and what allows us to see is just this very tiny portion in the middle here. That's what's the visible spectrum, where we see colored light, and allows us to see all the different colors that we get to see. But there's so much more to the spectrum out there. Over on this side, we have the very long wavelength. So there's our wavelengths here. And 10 to the 8 meters, for example, is, well, now I got to do math, 100 million meters in length. So very, very long. Remember, a wavelength is from one crest to another crest. So that's a super long wavelength. And down here are super short. 10 to the minus 16 is tiny, 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 tiny. And then our frequencies. Our frequency over here, this is just 10 wavelengths per second. And over here, this is 10 times 10 times 10 times 10, 24 times wavelength. So very, very high frequency. What I want you to see here on this spectrum is that this is long wavelength, low frequency. Shorter wavelength, higher frequency. Just what we talked about previously. And what I've done is I've broken up the electromagnetic spectrum into sort of different categories. So we've got radio waves, which are very long wavelengths. We've got microwaves, infrared waves, ultraviolet radiation, X-rays, and gamma rays. All of those are on the electromagnetic spectrum, and we're going to talk about what those are, what they do, and why we use them, and why they're important for us, and how we might use them. So that's our electromagnetic spectrum. Visible light is the colored part of the spectrum that we talked about earlier, this little thin section here. And visible light is the light we're able to see with our eyes, and it's also the light that allows us to see color. White light contains all the wavelengths of light in the visible spectrum. Remember, the visible spectrum is just this little narrow bit here, composed of that rainbow. Red light has the longest wavelength, and violet light has the shortest wavelength. And I put this back in here just so you guys can see that again, with the red having longer wavelengths and the violet having the shortest wavelengths, and then it just gets shorter as we move from red to violet. Obviously, the way we use visible light is it allows us to see. It allows us to see colors or lack of colors, those kinds of things. So that's our biggest use of it. Not all of the electromagnetic spectrum is visible to the naked eye, but it's still there. And we use different wavelengths to our advantage, but must also be cautious, as some can be quite harmful. So the waves that make up the electromagnetic spectrum are all forms of what we call electromagnetic radiation, or EMR. And EMR varies from wavelengths in the range of kilometers, like we would find in radio waves, to wavelengths in the nanometer range and even smaller. We will cover the kinds of electromagnetic radiation very briefly in the next section, and if you want to go through more and dig more detail, hit pause right now and maybe have a look at page 216, 217 of your textbook to go into a little bit more detail. So here are the different kinds, and we're going to work from on that spectrum that we had. We're going to work from the radio side over to the gamma ray side. And so radio waves are the longest wavelength, lowest frequency, and like the name suggests, we use them often in communication devices, like radios. So AM and FM radios, for example, or I think we talked in class about ham radios, which are even longer wavelengths, but travel a little further. We talked, remember, that AM radio has longer wavelengths, but it doesn't carry as much information, so you don't hear as good a quality of music that might come from an AM radio compared to an FM radio station. FM has a shorter frequency, or shorter wavelength, meaning a higher frequency compared to AM, and so it carries a little bit more information, which allows that that wave, or that frequency, to have a little bit more richness to the sound that you might get from an FM frequency. Microwaves, moving along on the spectrum, are shorter than radio waves in wavelength, but have a higher frequency. Now, as we increase the frequency, that basically means that per packet of light, or per packet of EMR, they're carrying more information or more energy per packet of that light. And what that means is we can do more with it. So, for example, with an AM radio signal, we get okay quality radio for us to listen to. For FM radio, because it's a shorter wavelength but a higher frequency, we can pack a little bit more energy in there, which means we can pack a little bit more information or better quality sound. In microwaves, we can pack a whole bunch more information. So we use microwaves, obviously. Our microwave ovens that we have in our houses are actually emitting microwaves, and what they basically do is they vibrate water in food, and they get that water excited so much that it heats up. Now, that's one way we can use them, but I think what's really cool is Wi-Fi and cell signals and all of those kinds of things are also microwaves as well. And if you've paid attention to or maybe even ask your parents about it, the different kinds of cell phones we've gone through in the last little while. We used to be on 3G networks, now we're on 4G networks. I think they're talking about 5G networks next. The G stands for gigahertz, and we're talking about different frequencies, higher frequencies, 3 to 4 to 5. We're getting higher frequencies, which means we're carrying more information per packet of radiation, meaning that we can get more stuff transferred faster. So a 3G network is much slower than a 4G network. And that's just because we can't cram as much information into a 3G packet than we can into a 4G packet. So it's kind of cool to think about that. Your Wi-Fi works off of this as well, and we can cram a fair amount of information per packet of energy in your Wi-Fi. So I think that's kind of neat, and a neat application as to how we're using electromagnetic radiation in our everyday lives. I mean, if you're sitting in your house and you're using Wi-Fi right now, there are electromagnetic waves bouncing all over the place. And there'll be a video that I'll link to in the resources section that sort of shows this a little bit, and it's kind of crazy to think about. We can't see these waves, but they're around us, and they're flying around all over the place, and they can move through walls, and they can move through the atmosphere, and they're what's carrying all of the little bits of information that are allowing you to take this video off the internet, put it onto your computer, and watch it come back. I think it's remarkable. Moving along are infrared waves, and infrared waves or infrared radiation is the next one closest to the visible spectrum, on the red side of the visible spectrum, and we can't see them, but they're still shorter wavelength. Again, we're getting close to being able to see them now, especially the longest infrared waves. We still can't see them, but we know they're there because we can sense them coming off of hot things. So we basically we use them to detect hotter and colder areas. We use them in infrared cameras and some night vision goggles. And what they do is basically those pieces of technology, we've designed a little sensor inside them that allows us to shine it at objects. And then that sensor translates how much infrared radiation is coming off of those objects and then turns it into visible light that we can see. And so if you shine, let's say, an infrared camera at something that is hot, it'll appear white or sort of in that red end of things, and that means it's very hot, and if it's cold, it's in the violet end of things. And all that camera has done is it's gathering the infrared radiation that's coming off of something that is hot or cold, If it's hot, there's lots of infrared radiation coming off of it. If it's cold, there's not much. And what it does is it gathers it, and then it transmits or transfers it over to what we can actually see. So there'll be a little screen, and it displays it in a way that we can actually see it. So that's infrared waves. We're going to skip over visible light. I've already talked about it. And we'll talk more about how we see using visible light in the next concept. Moving on past the visible spectrum on the violet end is ultraviolet or UV radiation. And as you guessed, we're getting even shorter wavelengths. Remember, the shorter the wavelength, the higher the frequency. The higher the frequency, the more energy per packet that we can carry. And ultraviolet radiation carries enough energy that it's actually able to burn skin and damage cells. And this leads to skin cancer. And so that's why we wear sunscreen, for example, when we are out in the summertime, because some ultraviolet radiation squeaks its way through the atmosphere and gets down to us. And it can actually cause damage to our cells because it carries so much energy per packet of light. What this means then is we have to be extra careful with ultraviolet radiation, and thankfully our atmosphere filters out most of the ultraviolet radiation that comes from the sun, but some of it gets through, and that's why we wear sunscreen and sunglasses, and maybe try to wear long pants on a hot day in the summertime. The last end of the spectrum, and I'm only going to briefly go over these, are X-rays and gamma rays. You've heard of X-rays before, and X-rays are used to take pictures of the inside of our body. Basically, they measure density differences inside of our bodies and allow us to see things like bones and if they might be broken or something along those lines. X-rays and gamma rays are even shorter wavelength, higher frequency than ultraviolet radiation, and so they carry even more energy per packet, and they can be very, very harmful depending on how much you're exposed to. So, if you went and got an X-ray every single day for the rest of your life, that's going to cause problems, because that amount of radiation can be damaging to cells in your body. That's why we try to limit the amount of X-rays that somebody might get. Gamma rays are even more harmful. And if you've read any science fiction, you've probably thought, well, Hulk is, Hulk because he's been exposed to gamma rays. Well, I mean, if you got exposed to that much gamma rays as Hulk did, you'd probably die. So I don't think you're going to, don't go out chasing gamma rays to think you're going to turn into a superhero. Anyway, we still use these waves, though, obviously, to our advantage in technologies. We know we use X-rays to look inside our bodies and look at densities and examine bones and other things. But we also use gamma rays to kill harmful cells as well. And hospitals and other places will use gamma ray machines to basically what we call irradiate or hit maybe surgical equipment with a whole bunch of this very harmful radiation to kill the cells on the surgical equipment so it can be used again. Basically to sterilize it and make it safe to use again. So we still use those rays. Again, for X-rays and gamma rays, they come off the sun as well, just like ultraviolet radiation, but we don't get any of that down here at the surface because our atmosphere and the magnetic field around Earth do a really good job of bouncing that stuff away from us so that we don't end up getting hit by it, because it's very harmful. So this is just another summary of what's going on with everything with the electromagnetic spectrum. This one, you'll notice, has been flipped compared to what was going on in the first diagram or image I showed you. So notice that radio waves are now on the left side and gamma rays are now on the right side. But it's showing you the wavelength and frequency here. This is what penetrates the Earth atmosphere. Yes, radio waves get through it. Microwaves, some of them get through, some of them don't. Yes, visible light gets through. Infrared light gets through because that's what warms us up from the sun. And really not much of this stuff from ultraviolet through to X-rays and gamma rays gets through. this gives you an idea of the size of these wavelengths. So we're talking about radio waves being the size of buildings. Um, you know, infrared are the size of the point of a needle, right? A wavelength is the size of a point of a needle. Our visible spectrum are the size of little tiny protozoans that are microscopic. And then we're getting into things that gamma rays are the size of the nucleus inside of atoms. So very, very, very tiny. And the rest of this is really not all that important for us. I just really liked this diagram and I thought I'd share it with you. So that's what's going on with that diagram there. So just a really quick message about some of the dangers, and I've already talked about these, so I'll go through this pretty quick. The higher the frequency or shorter wavelength, the more damaging the electromagnetic radiation that we encounter. Basically, we've said this is because the waves are more energetic. They carry more energy per packet of light as they get into a higher frequency, shorter wavelength situation. The more energy they carry, the more chance they have of damaging something. So it's for this reason we are most concerned with ultraviolet X-rays and gamma rays. Those are the ones that can do the most damage because they are at the end of the spectrum where those packets of light energy contain the most energy. And as I said earlier, our sun releases large amounts of these types of electromagnetic radiation, but our atmosphere and our magnetic field protect us from most of it. But like I said before, we need to watch out for getting too much sun or being exposed to too many X-rays in a short period of time. So that is a really quick lesson running through concept C4. And so what I'm going to do at this point is invite you guys to, go back and rewatch any of the sections if I went maybe a little too quickly for you, anything like that. And if you're comfortable with that, then what I would invite you to do is to go ahead and have a look at these resources. And this will be posted on the Google Classroom as well, where you access this lesson, so you can go and have a look at that too. So obviously, if you want to dig more deeply into this, go to your textbook, pages 212 through 229. There's going to be videos under the resources section for Unit C. So have a look at that under resources, videos, and other resources. I'm thinking I'll add in one more in here, veritasium. I just thought about it, and we'll talk about radiation a little bit. I'll add that video in. I think it's about 15 minutes long. I'll add that in for you guys. It's more than anything, you'll find it interesting. I really like the video. It's fantastic. Once you've had a look at all of that kind of stuff, then start to do these practice questions. So the ones out of the textbook, and then the worksheets that I will post. The worksheet you'll be able to find under resources, and then notes and worksheets under Unit C in the Google Classroom. And I will post a key to that in the next couple of days as well, if you'd like to check your answers and see how you did compared to what I thought you should do. And then finally, I will probably post a series, a Google form that'll have a series of formative or practice questions for you guys to try. Once you've done those formative questions on the Google Classroom, submit them to me. I will go over them, have a look at them, make sure that they look good, and then we can I can send you a message back and say, hey, everything looks good, and then at some point by the end of the week I'll have that summative assessment, another quiz, posted on the Google Classroom that you can try. Don't do the summative assessment until you've gone through and done these things here. Okay, there's no point in rushing into it. You've got lots of time. We'll get through this, at your own pace. If you've got questions, please fire me an email, pop onto office hours, and let's work our way through these, because I think it's important that we continue to be in contact together. So, pop online. The office hours will be done through Google Meet, so I'll have my face up there on the screen, and you're welcome to have your face up there on the screen, and we can chat and go over any questions that you might have. That's all I have to say for now. Fire me an email if you have any problems. And if anything I've done here so far hasn't worked for you, or you'd like more of something or less of something, send that my way too. I'm learning just as you guys are right now. So let's see if we can learn together and make the best of the situation that we're in right now. So stay healthy, stay away from each other, and we'll see you for C5 next week.